Okay, let's be totally honest for a second. Staring down a major college algebra exam, yeah, it can feel incredibly daunting. The formulas start blurring together, the graphs look like abstract art, and, well, that familiar wave of anxiety starts creeping in. But hey, take a deep breath because you are in exactly the right place. Welcome to this explainer. Think of this as your ultimate guided study session for Lecture 13. We're going to walk through exactly what you need to know, breaking down all that complex algebra into clear, visual steps so you can walk into that test feeling literally unstoppable. So here's our roadmap for this exam prep. Level 1, solving trig equations. Level 2, the fundamentals. Level 3, the vertical line test. Level 4, graph transformations. And finally, Level 5, calculating domains.
All right, let's dive into this. Module 1, Solving Trigonometric Equations.
Let's tackle a core trigonometric equation step by step. Okay, say we have 2 cosine theta plus sine squared theta minus 1 equals 0. Now, seeing that sine squared theta right next to a cosine theta, that is your immediate cue to use the Pythagorean identity. It's like a math reflex. So substitute sine squared theta with 1 minus cosine squared theta. Distribute that out, and the ones completely cancel, leaving you with negative cosine squared theta plus 2 cosine theta equals 0. From there, factor out the cosine theta, giving you cosine theta times the quantity negative cosine theta plus 2, all equal to 0. This gives us 2 potential solutions, where cosine theta equals 0 or where cosine theta equals 2. But wait, cosine theta equals 2? That's undefined, impossible. So your actual final answers are just the angles where cosine is exactly 0, which are pi over 2 and 3 pi over 2.
Moving right along, Module 2, the fundamentals, that's intervals, relations, and functions.
Look, so much of this just comes down to the brackets. When you see closed, hard square brackets, like bracket A, comma B bracket, that represents a closed interval. It literally means less than or equal to, so those endpoints are absolutely included in your answer. On the flip side, open parentheses, parentheses A, comma B, parentheses, mean strictly less than or strictly greater than, so the endpoints are totally excluded. If it helps, picture solid dots for closed brackets and empty circles for open parentheses. Seriously, nailing this notation early on is such an easy way to save points on the exam. Next up, we really need to strictly define what a relation is. Honestly, a relation is simply any set of ordered pairs, an x and a y. It's just a mapping. For example, a set containing the pairs 1, 2 and 1, 4. It can also be expressed as an equation, like x equals y squared. There are no strict rules here about uniqueness. It's basically just any connection between inputs and outputs. Let's visualize what a relation actually looks like when we graph x equals y squared. Picture a standard coordinate grid in your head. Starting right from the origin at 0, 0, this equation creates a sideways U-shaped parabola that opens up to the right. Now notice something here. For an x value of 4, the graph splits, right? It gives you a y value of positive 2 up top and a y value of negative 2 on the bottom. It's a perfectly valid relation, sure, but as we're about to see, it breaks a fundamental rule to be considered something more. And that brings us to the function. A function is way stricter than a relation. It is a rule that assigns a unique output to each input. That word right there, unique, is the whole shebang. You absolutely cannot have one input pointing to 2 different outputs. We also define 2 really key sets here, the domain, which is the set of all valid defined inputs, or x values, and the range, which is the specific subset of outputs, the y values, that the function actually produces. Okay, moving on to our next key concept, Module 3, Visual Gymnastics, the vertical line test. So how do we instantly tell if a graphed relation is a true function? We use the vertical line test, of course. Imagine a blue upward-facing U-curve. If we drop several vertical lines straight down through it, each line intersects that curve at exactly one single point. Because it never hits twice, bam, it passes the test. It's a function. Now imagine a sideways oval. When we drop a single vertical line straight down through that, the line pierces the oval twice, once at the top and once at the bottom. Because it intersects at more than one point, it completely fails. It is merely a relation, not a function. Let's build on that. Module 4, Applying Graph Transformations. Before we can even think about transforming a graph, we absolutely have to know our anchor shapes. You need to instantly recognize the straight diagonal line passing through the origin as y equals x. You need to know that the classic symmetrical U shape is the parabola y equals x squared. And you should definitely recognize that smooth, flowing S-curve crossing through the origin as y equals x cubed. These are your starting blocks. Get these memorized for sure. Okay, once you have those anchor shapes locked in, you just apply these exact rules. Adding a constant number outside the function, like f of x plus 3, shifts the whole graph straight upward by 3 units. Pretty intuitive, right? But if you modify the x inside the parentheses, watch out, because it behaves the total opposite of what you might intuitively think. F of parentheses x minus 3 actually shifts the graph 3 units to the right, not left. And a negative sign outside, like minus f of x, just reflects it perfectly upside down across the x-axis. Honestly, mastering these rules is literally like getting the cheat codes to the test. Let's treat this like an interactive puzzle. Imagine a central blue parabola labeled f just sitting gently in the first quadrant. Scattered all around it in the other quadrants are 5 target parabolas, numbered 1 through 5. They're all the exact same parent shape. They've just been shifted, flipped, or stretched. If you get a problem like this on the exam, your main job is to track the journey of the vertex, the very tip of the parabola, from the blue original to the new target. Let's reveal a few of those solutions. So graph 3 moved purely along the horizontal axis, right? So its equation is y equals f of parentheses x minus 4. It just shifted 4 to the right. Graph 1 went straight up, so we add 3 on the outside, y equals f of x plus 3. But look really closely at graph 5. It's tricky because it requires stacking multiple transformations. First, it shifted 4 units to the left, which gives us an x plus 4 on the inside. Then, the whole thing flipped completely upside down, meaning we need a negative sign on the outside of the function. So putting it all together, graph 5 is y equals negative f of parentheses x plus 4. All right, let's apply this stacking concept to a much harder problem from your class activity. Consider our parent function, a blue semicircle sitting flat on the x-axis between 0 and 3. Its equation is kind of complex. Y equals the square root of 3x minus x squared. The problem asks us to find the specific equation for a target graph. Visually, we can clearly see the target graph is an upside-down semicircle that's been pushed way over to the left, now sitting between -4 and -1, and it's shifted below the x-axis. Let's walk through the exact algebraic steps to solve this together. First up, we shift 4 units to the left. We do this by replacing every single x in the original equation with the quantity x plus 4. Next, we deal with that upside-down reflection across the x-axis by multiplying the entire function by -1. Finally, the graph was shifted downwards by 1 unit, so we simply subtract 1 from the very end of the whole expression. When you carefully expand the algebra, squaring the x plus 4 and combining all your like terms, you arrive at the final complex target equation, negative square root of negative x squared minus 5x minus 4, all minus 1. Excellent work so far. Let's actually lower the pacing for just a second. We've mapped relations, tested functions, and shifted graphs across planes. But this brings us to a really critical pivot question for your exam. What happens when the algebra itself threatens to break? Like, how do we find the natural domain when a function has a restrictive feature, say a square root, or a fraction that risks division by 0?
Here we go. Module 5, the final boss. Calculating natural domains.
Now, what's really interesting about this next part is the sheer variety of algebraic threats we face when finding a domain. We're asked to find the domain for 4 completely different functions. Function A is a simple x cubed, so no threats there. Smooth sailing. But look at the others. Function B is a rational fraction, meaning we gotta watch out for division by 0. Function C is tangent x, which has all those hidden asymptotes. And function D is a complex quadratic hiding inside a square root. F of x equals the square root of x squared minus 5x plus 6. Let's really break that last one down. Here is exactly how you methodically execute the solution. Step 1, establish the core rule. The expression inside an even radical, like a square root, absolutely must be non-negative. It cannot be less than 0. Step 2, we set up the inequality based on that rule. X squared minus 5x plus 6 must be greater than or equal to 0. Step 3, we use our factoring skills to find the roots. This factors out beautifully to the quantity x minus 3 times the quantity x minus 2, which is greater than or equal to 0. By testing our intervals, step 4 gives us our final natural domain. From negative infinity up to and including 2, union with 3 up to positive infinity. And summarizing the other problems, the logic holds totally steady. For our rational function, division by 0 forces us to explicitly exclude specific x values. If the denominator is x minus 3, our domain is quite simply all real numbers where x does not equal 3.
Simple as that. For the trig function tangent x, well, because it's sine over cosine, we must exclude any x value that makes cosine 0, which happens to be the odd integer multiples of pi over 2. It's all about finding exactly where the math breaks and drawing a strict boundary line right there.
Let's visualize what calculating a complex domain actually looks like graphically, using the function 1 over the square root of 4x minus x squared minus 3. We calculated the domain algebraically to be strictly between the x values of 1 and 3. And geometrically, this means the actual function curve only exists between the vertical lines of x equals 1 and x equals 3. Anything outside that window simply does not exist, because it would result in an imaginary number or a division by 0. The visual perfectly proves our algebra. It's like a giant puzzle coming together.
Just look at what you've accomplished today. You've mapped out trig patterns, defined strict functions, flipped graphs across coordinate planes, and calculated exact domains to keep the algebra from breaking down. You have officially mastered the material in this explainer. But remember, these aren't just arbitrary rules for a test. These are the fundamental codes that describe the physics of our universe. So now that you can manipulate the math this well, what real-world problem are you going to solve with it next? Good luck studying, and honestly, you are going to absolutely crush this exam.